Deep within the underground laboratories of the Large Hadron Collider, Dr. Marcus Thompson adjusts the final parameters for an experiment that has consumed 5 years of his life. Tonight, his team will attempt to recreate the conditions that existed in the universe just 1/1,000,000th of a second after the Big Bang. A moment so brief that light could barely travel the width of a proton. But as the massive particle accelerator hums to life, accelerating protons to nearly the speed of light before smashing them together with unprecedented energy, Marcus is troubled by a disturbing realization. Each collision will produce exotic particles that existed in abundance during the universe's first moments, but have since vanished completely from the natural world. The universe, it seems, has systematically forgotten how to create the very building blocks from which it was originally constructed. The symmetries that govern the primordial cosmos have been broken. The fundamental forces have separated into distinct interactions, and entire classes of particles that once filled all of space have decayed into oblivion, leaving behind only the faintest traces in cosmic ray showers and laboratory experiments. This profound transformation forces us to confront one of the most unsettling questions about our cosmic origins. Is the universe systematically erasing the evidence of its own birth? And if so, what other crucial information about the nature of reality might already be lost forever? To understand this cosmic amnesia, we must journey back to the very beginning, to an epoch when the universe bore no resemblance to the structured cosmos we observe today. In the first fraction of a second after the Big Bang, the entire observable universe was compressed into a region smaller than a single atom, filled with exotic matter and energy at temperatures so extreme that the fundamental laws of physics themselves were different from those we know today. During this primordial epoch, the 4 fundamental forces that govern our modern universe, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single primordial interaction. Matter and antimatter existed in perfect symmetry, while particles that have no analog in today's universe freely transformed into one another through processes that would violate every conservation law we hold sacred. The universe was, in essence, a quantum playground where reality itself was fundamentally malleable. As the cosmos expanded and cooled, this primordial perfection began to unravel through a series of phase transitions that cosmologists call spontaneous symmetry breaking. Like water freezing into ice, the universe passed through critical temperatures where its fundamental nature changed irreversibly. Each transition left behind a different cosmos, one step further removed from its original, unified state. The first of these transitions occurred when gravity separated from the other forces, creating the space-time fabric that would eventually curve and warp to form the cosmic web we observe today. This moment, occurring roughly 10⁻43 seconds after the Big Bang, marked the end of what physicists call the Planck epoch, a time when quantum effects dominated even gravity itself, and the very notion of space and time as we understand them may not have existed. The evidence for this cosmic metamorphosis doesn't come from direct observation. The light from these early moments has long since been redshifted beyond detection, but from the mathematical structure of modern physics itself. The standard model of particle physics, that remarkable theoretical framework that describes all known particles and their interactions, bears the scars of these ancient symmetry breakings like fossil imprints in cosmic stone. Dr. Lisa Randall's pioneering work at Harvard has shown how extra dimensions of space, if they exist, might hold the key to understanding these lost symmetries. In her theoretical models, the forces that appear separate in our familiar three-dimensional world are actually unified when viewed from the perspective of higher-dimensional space. But these extra dimensions, if they exist at all, are curled up so tightly that they're completely inaccessible to direct observation, hiding the universe's true unified nature from anyone confined to our dimensional slice of reality. The Large Hadron Collider's experiments provide tantalizing glimpses of this hidden unity. When protons collide at energies approaching those present in the first moments after the Big Bang, they briefly recreate conditions where some of the universe's lost symmetries might be partially restored. The exotic particles produced in these collisions, strange quarks, muons, tau particles, and dozens of other ephemeral entities, exist for mere microseconds before decaying into the stable matter we know today. Yet each of these fleeting particles carries information about the universe's forgotten past. The muon, for instance, is essentially a heavy electron that serves no apparent purpose in the modern cosmos. Its existence suggests that in the early universe, there were multiple varieties of every fundamental particle we observe today, all related by symmetries that have since been broken. The muon is like a cosmic fossil, a remnant of a time when the universe had far more diversity in its fundamental building blocks. The story becomes even more mysterious when we consider antimatter. According to our best theories, the Big Bang should have produced equal amounts of matter and antimatter, particles that annihilate each other on contact, releasing pure energy. Yet our observable universe consists almost entirely of ordinary matter, with antimatter appearing only in high-energy cosmic ray interactions and particle physics experiments. Somehow, during the first second after the Big Bang, the universe developed a slight preference for matter over antimatter, a bias so subtle that it amounted to just one extra matter particle for every billion matter-antimatter pairs. The Planck satellite's exquisitely detailed map of the cosmic microwave background radiation provides our best window into this matter-antimatter asymmetry. The tiny temperature fluctuations in this ancient light, the afterglow of the Big Bang itself, carry the statistical signatures of the processes that created the universe's matter content. But the mechanism responsible for this cosmic bias remains one of physics' greatest unsolved mysteries, a piece of information that the universe seems determined to keep secret. Dr. Andrei Sakharov's groundbreaking work in the 1960s identified the conditions necessary for the universe to generate more matter than antimatter. Violations of certain fundamental symmetries, interactions that don't respect the arrow of time, and departure from thermal equilibrium. All of these conditions were likely met in the early universe, but the specific processes involved have left no direct traces in the modern cosmos. The universe has forgotten how it solved the riddle of its own existence. This cosmic forgetfulness extends beyond particles and forces to the very structure of spacetime itself. During the first fraction of a second after the Big Bang, the universe likely underwent a period of exponential expansion called cosmic inflation. In less than 10⁻30 seconds, space itself expanded by a factor of at least 10^26, stretching quantum fluctuations to cosmic scales and setting the stage for all the structure we observe today. The Laser Interferometer Gravitational Wave Observatory has opened an entirely new window into these primordial processes. Gravitational waves, ripples in spacetime itself, can travel unimpeded from the earliest moments of cosmic history. If inflation occurred as theorists predict, it should have generated a background of gravitational waves that still permeates the universe today. But detecting these primordial gravitational waves requires extraordinary sensitivity, as they've been stretched and weakened by billions of years of cosmic expansion. The recent detection of gravitational waves from colliding black holes and neutron stars has proven that these spacetime ripples exist and can be measured. But the primordial gravitational waves from inflation, if they exist at all, are predicted to be millions of times weaker than anything LIGO can currently detect. The universe's memory of its own inflationary birth may forever remain beyond our technological reach. Even more troubling is the possibility that cosmic inflation itself erased crucial information about what came before. If the universe underwent exponential expansion, any structures or patterns that existed prior to inflation would have been stretched far beyond our cosmic horizon. The observable universe might represent just a tiny, causally disconnected patch of a vastly larger cosmos, one whose global properties we can never hope to determine. The James Webb Space Telescope's observations of the most distant galaxies provide another perspective on cosmic memory loss. These ancient systems, seen as they were when the universe was less than 1 billion years old, reveal conditions that no longer exist anywhere in the modern cosmos. The first stars were massive giants that burned through their nuclear fuel in just a few million years before exploding as hypernova. The first galaxies were chaotic, actively forming stars at rates hundreds of times higher than anything we observe today. The first supermassive black holes grew through processes that seem to violate everything we understand about black hole formation. Yet the specific mechanisms that created these primordial objects have been erased by billions of years of cosmic evolution. The first stars have long since exploded, enriching the universe with heavy elements but destroying all direct evidence of their formation. The first galaxies have merged and evolved beyond recognition, their original structures lost in the chaos of cosmic collisions. Even the supermassive black holes at galactic centers have grown so large that their formation histories have been completely obscured. Computer simulations provide our best tool for reconstructing these lost processes, but they rely on assumptions about physics that we cannot directly verify. The Millennium Simulation and its successors can recreate the formation of cosmic structure in exquisite detail, following the evolution of dark matter, gas, and stars across billions of years. But these simulations are only as reliable as the physical models they incorporate, and many crucial processes, such as the formation of the first stars or the growth of primordial black holes, remain poorly understood. The cosmic microwave background radiation itself, that ancient light from 380,000 years after the Big Bang, represents a fundamental limit to our ability to observe the universe's earliest moments. Before this cosmic dawn, the universe was opaque to photons, filled with ionized plasma that scattered light in all directions. Everything that happened in the first 380,000 years of cosmic history is hidden behind this wall of fire, accessible only through indirect evidence and theoretical inference. Recent discoveries in neutrino astronomy offer a tantalizing possibility for piercing this cosmic veil. Neutrinos interact so weakly with matter that they can travel unimpeded from the earliest moments after the Big Bang. The cosmic neutrino background, a sea of ancient neutrinos predicted to fill all of space, should carry information about the universe when it was just 1 second old. But these relic neutrinos have been cooled by cosmic expansion to temperatures just above absolute zero, making them extraordinarily difficult to detect with current technology. The IceCube Neutrino Observatory, buried deep in Antarctic ice, has demonstrated that high-energy neutrinos from distant cosmic sources can be detected and traced back to their origins. But the primordial neutrinos from the Big Bang are billions of times less energetic, requiring detection techniques that push the limits of what physics allows. If we could somehow observe the cosmic neutrino background directly, it would provide an unprecedented window into the universe's first second of existence. Dark matter adds another layer to this cosmic mystery. Whatever particles comprise the universe's dominant matter component, they interact so weakly with ordinary matter that they've left virtually no direct traces of their properties. Underground detectors like the Large Underground Xenon experiment have spent decades searching for dark matter particles. But despite increasingly sensitive instruments, these mysterious entities remain as elusive as ever. The absence of dark matter detection might itself be a form of cosmic amnesia. If dark matter particles were created in the hot, dense conditions of the early universe, their properties were determined by physics that no longer operates in the modern cosmos. The specific mechanism that produced the observed abundance of dark matter, roughly 5 times more than ordinary matter, represents another crucial piece of information that the universe has seemingly forgotten. Cosmic inflation theory suggests an even more radical possibility, that our entire observable universe might be just one bubble in a vastly larger multiverse, where different regions have undergone different patterns of symmetry breaking and ended up with fundamentally different physics. In this scenario, the specific properties of our cosmic patch, the strengths of the fundamental forces, the masses of particles, the dimensionality of space, might be just random outcomes in a cosmic lottery with no deeper significance or explanation. The European Space Agency's Planck mission has searched for evidence of this multiverse by looking for circular patterns in the cosmic microwave background that might indicate collisions with other bubble universes. So far, no such evidence has been found, but the absence of detection doesn't rule out the possibility. If other universes exist beyond our cosmic horizon, they represent information that is fundamentally inaccessible lost not just to observation, but to the very structure of spacetime itself. Perhaps most unsettling is the possibility that the universe's memory loss is ongoing and accelerating. The mysterious dark energy that drives cosmic expansion appears to be stretching space itself at an ever-increasing rate. As galaxies recede from one another, their light becomes increasingly redshifted until it eventually disappears beyond detection. In roughly 100 billion years, all galaxies beyond our local group will have receded beyond the cosmic horizon, leaving future observers with a universe that appears to contain only their immediate neighborhood. This cosmic horizon represents a fundamental limit to information preservation. Any evidence of cosmic processes occurring beyond this boundary will be permanently lost, erased by the expansion of space itself. Future civilizations will inhabit a universe that appears increasingly empty and isolated, with no way to reconstruct the rich cosmic web of galaxies, clusters, and large-scale structure that we observe today. The heat death of the universe, predicted to occur in roughly 100 years, represents the ultimate form of cosmic amnesia. As the last stars burn out and even protons decay into elementary particles, all organized structure will disappear, leaving behind a cold, empty cosmos filled only with elementary particles and photons. At this point, the universe will have forgotten not just its birth, but its entire history of cosmic evolution. Yet even in this seemingly hopeless scenario, quantum mechanics offers a strange form of hope. The Poincaré recurrence theorem suggests that in a finite universe, given infinite time, quantum fluctuations will eventually recreate any configuration of matter and energy that has ever existed. The universe might, quite literally, remember its pass through the random motion of particles across unimaginable spans of time. But these quantum memories would be fleeting and random, bearing no connection to the causal chain of events that created them originally. A quantum fluctuation might spontaneously create a perfect replica of Earth, complete with all its history and inhabitants. But this replica would be a cosmic accident rather than a continuation of our actual evolutionary story. Standing in that underground laboratory, watching protons collide at energies that briefly recreate the conditions of the early universe, Dr. Thompson is participating in humanity's attempt to recover some of the cosmos's lost memories. Each particle collision is like an archaeological dig, uncovering evidence of physics that operated when the universe was young and the fundamental forces were still learning how to be separate. The standard model of particle physics, for all its spectacular successes, is clearly incomplete. It cannot explain the existence of dark matter, the dominance of matter over antimatter, or the specific values of fundamental constants that allow complex structures like stars, planets, and life to exist. These gaps in our understanding represent information that the universe has hidden from us, perhaps permanently. Yet the search continues. The next generation of particle accelerators, space-based gravitational wave detectors, and cosmic ray observatories promise to push deeper into the universe's forgotten past. Each new discovery is a small victory against cosmic amnesia, a recovered fragment of information about how our universe came to be the way it is. Perhaps the most profound aspect of this cosmic memory loss is what it reveals about the nature of information itself. In a universe governed by quantum mechanics and general relativity, information cannot be created or destroyed, it can only be transformed or hidden. The universe's apparent forgetfulness might be more accurately described as cosmic encryption, where the information about primordial processes still exists, but has been encoded in forms we don't yet know how to read. The holographic principle, emerging from studies of black holes and string theory, suggests that all the information in any volume of space might be encoded on its two-dimensional boundary. If this principle applies to the universe as a whole, then all the information about cosmic history, including the processes we think have been forgotten, might still be present in the structure of spacetime itself, waiting for us to develop the theoretical tools needed to decode it. As we continue our quest to understand the universe's origins, we're racing against cosmic expansion itself. Every day, more information disappears beyond our cosmic horizon, lost to the accelerating expansion of space. We are archaeologists working in a library where the books are constantly being erased, trying to piece together the story of existence before the evidence vanishes forever. In this race against cosmic forgetting, every observation becomes precious, every theoretical insight a potential key to unlocking the universe's deepest secrets. We may never fully recover all the information that has been lost to cosmic evolution, but our very ability to ask these questions represents something unprecedented in cosmic history. Matter organized into forms capable of contemplating their own origins and mourning the loss of cosmic memory. The universe may be forgetting its own history, but through our observations and theories, we are helping it remember.